Okay, let's just take a look at a series RL circuit review. So we're going to start with our drawing right here, and we're going to note that K means 1,000 here, and M is your milliamp. So you got to remember to keep your decimal places in mind. So the drawing, well, we're going to have an AC source right here, and apparently we've got a resistor, and we got an inductor there like that. Okay, and so this is 2,000 kilohertz. I'm going to go ahead and write this as 2,000 hertz. And we know that my I total is 1 milliamp, so I'm going to go ahead and write that as 0.11 amps. And 1,500, 1.5 k ohms, I'm going to go ahead and write that as 1,500 ohms. And my I got 0.5 henries right here. So that's what that is going to look like. So we'll start with my XL, which is going to be 2 pi frequency times my inductance. So this is pretty high frequency, so that's going to have some pretty high inductive reactance. 2 pi, 2,000 henries, or 2,000 frequency times 0.5 henries is going to give me 62.83, 6,283.18 ohms. So there's my first one right there. Okay. My voltage of my resistor, and so my voltage here and my resistor drop is real, and we can measure that, and it's going to be my current of the through the resistor times resistance. So this is a series circuit, so we have 0.001 amps, so that's going to be pretty easy to know that 0.001 amps is flowing through each of these devices. So that's going to be 001 amps times my resistance, which was 1,500 ohms. And you run that in the calculator, that's going to give you 1.5 volts. Okay. My voltage drop on my inductor, so that's going to be a similar formula. It's going to be the current times the inductive reactance. And so because it's a series and my current stays the same, we're just going to bring that 001 amps down, and we're going to multiply it by 6.2, what we found right there, 6283.18, and that's going to give us 6.283 volts. Okay. And then I'm going to get my voltage total. And so we have some, I guess, imaginary voltage and some real voltage drops there. And there's going to be the square root of my voltage of my resistor squared plus the voltage of my inductor squared, which is going to give us 1.5 volts plus 6.283 volts. Remember, these are squared. And if I square those and add it, square that and add it and take the square root, I get 6.4597 volts. Okay. My total impedance is going to be the resistance here that's measurable, and the square root of that, plus the inductive reactance squared, and we'll take the square root of that. So this is going to be the square root of 1,500 squared plus 6283.18 squared. And if you run those numbers right there, you take the square root of it, you get 6459.75 ohms. Okay. My phase angle, it's related to my power factor. So remember, my power factor is going to be R over Z. And so the resistance here on 1,500 ohms on my resistor, so I'm going to get some power dissipation here. That's work. This is the real work. This is the real item that we can measure that we're getting out of this. But we're actually going to have to pay for a little more electricity than we're actually using, because we have some inductance in here that is kind of wasteful. It's nothing we can do about it. And so what we are going to do is kind of figure out how much, what percentage of real work versus total work or watts that we're paying for. Okay. And so what we have here is 1,500 ohms for that resistance, and we have right here, my totals impedance was 6459.75 ohms, and you divide that, I get 0.2322, which is 23.22%. So this isn't a very efficient circuit at all. We're paying a lot for a lot of extra power or VA from what we're actually getting out for work out of that load right there. And so I want the angle. Remember that angle is equal to cosine of 0.2322, and that is 76.57 degrees. Yeah, it's not a very good angle. We would like to get this as close to 0 as possible, so that the amount that we're being billed for is going to be as close as possible as the amount that we're actually getting out of this circuit. Okay. My power, so this is real, and it's VR times IR. This is what we're getting out of the circuit that's positive, and we're going to have 1.5 volts from up here, and we're going to times it by 0.001 amps because that stayed the same, and we get 0.0015 watts of the good stuff. But we have inductive reactants. Now this is the stuff that it's just part of the circuit, and it's costing us money because we're not getting any work out of it. So we have our voltage of our inductor times our current of our inductor, and so we had 6.283 volts, and we had 0.001 amps, and so that is equal to 0.00628 var. Okay, so there we go on that. And then we have our S, which is our total voltage times our total current, which is going to be 6.4597 volts times 0.001 amps, and that is 0.0064597 VA. And the other way we could have did this is we could have taken the square root of P squared and Q squared and given us our S. Okay, and let's just do another little check right here that I like to do. We have our power over S, our real power that we're getting over our apparent power here, 0.0015 watts over 0.0064597 VA, and you divide those out, you get 0.2322, which is right there, and that seems to check out okay. So not really a very efficient circuit we got going there. Plot the voltage triangle, and we come down here. We're going to need some scale or something, and maybe each one of these is equal to 1. So 1, 2, 3, and we need this kind of equal the same. 1, 2, 3, 4, 5, 6, 7. And so we have 1.5 volts of our real work here. So we're going to be 1.5. It's going to be here somewhere. And then the Q to the inductor, our voltage on our inductor was going to be 6.283. So we go 6.283. It's going to be up here somewhere, and that's where they cross. And if I draw that right there, so that's what I'm ending up here with. There's 6.283 in volts, and this was 1.5 volts across here. And remember that gave us 6.4597 volts. That was what this represents, and this was at an angle of 76.57 degrees, which, like we said, we'd really like that angle down here somewhere to bring down this imaginary leg right here. But this imaginary leg is very, very large, and so this is not, this would need some power factor correction.